Welcome to the Introduction to FHIR for Research webinar. On the webinar today, we'll be talking about FHIR for Research in two different parts. The first part is a high-level introduction. We'll talk about the high-level characteristics of FHIR and how they're relevant for research. We'll talk about some possible research applications for FHIR, looking at some papers that have been recently published using FHIR. We'll talk about why FHIR has been broadly adopted in the health IT world and how this impacts FHIR's research applications. And we'll talk a little bit about how FHIR fits into the ecosystem of other standards and data models. In the second part, we'll touch on medical terminology and how that works with FHIR to improve semantic interoperability. We'll cover using FHIR to represent data with resources and how constraining rules and extensions can customize FHIR to be used for specific use cases. And we'll talk a little bit about how data can be accessed via the FHIR API. For the first part, the introduction to FHIR for research, we'll start off by talking about the FHIR standard at a high level. So FHIR is a standard for exchanging health information electronically. Standards like FHIR help to establish a common language and a common process for health information technology systems, which allow these systems to communicate with each other and share information more seamlessly and efficiently. FHIR stands for Fast Healthcare Interoperability Resources. The FAST refers to designing and implementing FHIR. One of the design goals of FHIR was to specifically to make FHIR easier to work with from an implementation standpoint. And then resources refers to building blocks. And we'll be talking a lot about resources in the rest of this webinar. FHIR is a free standard that is open to use. It's developed as part of an open standards process. Again, resources are those building blocks that allow solutions to be built from FHIR with these modular components. And FHIR can be customized. It's built into FHIR's design actually through some capabilities called extensions and profiling. And we'll talk about those a little bit more later on in the webinar. To give you a sense of what kinds of resources are available in FHIR. This is a screenshot from the R5 release of FHIR. That's the most recent release of FHIR, showing part of the list of resources. Actually, it's hard to read already on this slide, and it's too long to fit on one slide. But this just gives you an idea of the scope of health data that FHIR covers. So there's some things at the bottom that you might expect, like observations, specimen, body structure, a bunch of different medication-related resources. There's patient resources as well. And then there's a lot of other resources too that might be a little less expected. So for example, there are a bunch of resources related to implementing FHIR itself. Those are at the very top. And then there are a number of other resources that are more specific. So for example, there's resources around immunizations, resources related to communication. There's a whole wide variety of data that are covered by FHIR. This is a diagram of the FHIR information flow. So typically when systems use FHIR, there's a FHIR client. Over on the left there, we have a couple examples of this. There could be an app, it could be a user interface on a computer, it could be a backend server. These clients can then request FHIR information from a FHIR web server. Those requests go over the HTTP RESTful API. This is common web technology. It's not just something that's used by FHIR. We'll talk a little bit more about how FHIR leverages common web technology, both for the RESTful interface and also for other aspects of FHIR. The FHIR web server, it could be part of an EHR, or it could be a standalone server, and the FHIR web server can communicate with underlying data systems that store the data, and would then convert those data into FHIR format and send that back to the FHIR client. So an example of a FHIR client is the health app on an iPhone that uses FHIR to connect to a patient's provider's EHR to pull down data. Could also be a research application It could be something like a clinical decision support system that gets integrated into an EHR. And all these use the same underlying approach for asking for data from the FHIR server and for formatting that data for sending back and forth. I'll talk a little bit now about where FHIR came from. So you might have heard of HL7v2 or HL7v3. So HL7 is a health standards body. They're responsible for developing FHIR and for maintaining FHIR, and also for some of the other key health IT standards that are used both in the US and also internationally. V2 is around 30 years old now, and it was designed for point-to-point messaging. It was limited to messaging like orders and transfers and couldn't handle complex interoperability like we'll talk about with FHIR, like connecting custom clinical decision support systems directly into an EHR. HL7v3 was developed to provide a replacement for V2 that was more flexible and address some of the other issues with interoperability around V2. However, in practice, V3 was pretty hard to implement. So it isn't widely used except for one exception that I'll touch on a little bit later. FHIR came out of these standards that really tried to take the lessons learned from these standards and develop a new standard that was easier to implement, easier to use, and also used the same kind of technology that was already used across the tech industry and not just limited to healthcare. So later on in the webinar, we'll talk about how JSON and XML are used to format FHIR data. I've already mentioned the RESTful interface that goes over HTTP, the same technology we use for accessing web pages. And then OAuth and OpenID Connect are authentication and authorization standards that are also widely used on the web. To put the timeline of FHIR into a little bit of perspective here, FHIR was first introduced in a blog post on Graham Greaves' blog. He's the main architect of FHIR at HL7. This was back in 2011. And since then, there's been a regular cadence of updates to the FHIR specification. The most recent update was in March of this year. That was the FHIR R5 release, which I'll be referring to when we talk about specific parts of that FHIR specification. And I've highlighted the word normative here on the slide. Normative means that the resources that have that flag attached to them are considered mature enough to not really need any more changes going forward. And this is just a signal for the level of maturity. It is one of the reasons why now is a good time to start looking at how FHIR can be used for research, because it really is getting to that point where at least some of the key parts of the specification are quite mature and also getting pretty well adopted. So before we talk about the adoption of FHIR, I wanted to go through a few examples of how FHIR is actually being used in published literature. This isn't meant to be a comprehensive overview of all the ways that FHIR could possibly be used in research. This is really just trying to pick a few representative papers from the last several years that have used FHIR. So I'll go through just very quickly through these 4 papers here. There are links to all of these papers and a few more at that URL on the slide there. And I'll show that URL again with the QR code at the end of this if you want to try to look at any of these references. So the first paper uses FHIR to fill clinical trial case report forms. These are forms that typically have to get filled out by a coordinator during a clinical trial. In this study, it basically was a proof of concept looking at 40 patients in a COVID trial at Vanderbilt, and it used EHR data to fill the case report forms using FHIR. There was a total of almost 12,000 values that could be populated with FHIR out of these for these 40 patients, and 84% of those were populated with data from the EHR using FHIR, and these had 89% concordance with human data entry, and the mismatches were actually often due to the data entry error. So the flow diagram on the right-hand half of the slide, this is a figure 1 from the paper. This shows just for the first 10 participants in the trial, a breakdown of what happened with the matching of these data elements. So for those first 10 patients, 93% were exact matches. For the fields that were mismatched, 6% were due to coordinator error. So this is human data entry error. And then just a few were due to issues with the underlying EHR data. The second study I want to talk about used FHIR to define portable phenotype definitions for developing a cohort. So phenotyping is an approach to algorithmically identify characteristics of patients based off of data in an EHR. For example, identifying whether a patient has a specific disease might be done by looking at a combination of lab reports and symptoms that are reported. This paper used FHIR and another technology called CQL, which stands for Clinical Quality Language. And CQL is a way of expressing clinical knowledge and logic in a format that can be executed by software. So using a combination of FHIR and CQL, this paper developed phenotype definitions, which were then validated at 3 other institutions. So the phenotypes were developed at University of Washington, Seattle, and then implemented at Mayo, Northwestern, and Cornell. And we'll see on the next slide that enlarges this this figure from the paper that the authors actually ended up using a translation layer to translate the FHIR and CQL to OMOP. Because all these 3 institutions had OMOP databases already, and they were able to leverage an existing translation tool to go from FHIR and CQL to OMOP. This is useful because not all institutions have OMOP databases, or they may have another database that that is not OMOP. And by using FHIR as essentially and CQL as a common way to represent the phenotype, it's possible to execute the phenotype not only on directly on a FHIR server, but also on different common data models. Here's that figure from the paper blown up so you can actually see it. So you can see University of Seattle was where they developed using this workbench application of phenotype. They published this in PhiKB, which is an online phenotype repository. And then this was sent out and executed at Northwestern, at Mayo, and at Cornell in a few different ways that were specific to those institutions. And they were successful in being able to execute the phenotype at all 3 institutions. A third example of use of FHIR in research is integrating patient-reported data into an EHR. So in this paper, the authors integrated data from a mobile application for COVID-19 symptom self-tracking, and they integrated this into Yale's EHR using Smart on FHIR. They were able to successfully record patient-reported data like oxygen saturation into the EHR. And this paper has a really good discussion of the IT challenges and solutions that they found. So if you're interested in this kind of data integration, it's worth taking a look at this paper. Finally, the last paper I'll talk about in this set of examples is a clinical decision support integration. The authors integrated an AI model for predicting likelihood of alternate treatment strategies for type 2 diabetes into University of Utah's EHR. This was again with Smart on FHIR. And this is a screenshot of one of the figures from the paper showing what the interface actually looks like inside the EHR. What's interesting about this is with Smart on FHIR, the authors were able to get data from the EHR for the specific patient, send that over to the AI tool. The AI tool was able to deliver these recommendations customized for that patient, and then this was able to be directly integrated into the EHR. Here are a few additional papers. These are also linked on that webpage I linked to before, and I'll show the URL again on the next slide. The first of these is another paper on clinical trial case report forms. This is another example of just being able to replace some of that manual data entry with data directly from an EHR via FHIR. The second one is another example of patient-reported data. And then the last paper is a review article talking about clinical decision support in FHIR, which is also worth taking a look at if you're interested in that. So all these papers are linked to at this URL, and that QR code will also take you to that URL. All right, next I'll talk a little bit about the current state of FHIR adoption. This map shows FHIR adoption as of 2019. Unfortunately, there's not a more up-to-date map available, but in 2019, this shows that 87% of hospitals and 69% of these clinicians use EHRs that were certified for HL7 FHIR. We have some more recent data that shows that around 78% of clinicians now have EHR software that supports FHIR, and the 5 leading EHR vendors include support for FHIR, and these cover 55% of all clinicians. So FHIR is now quite widely available, and especially most large health systems are running EHRs that support FHIR. There are a couple of factors that are driving FHIR adoption. One is the 21st Century Cures Act. And ONC is the Office of the National Coordinator for Health Information Technology. They're the ones who are responsible for implementing the Health IT certification program. And this, in conjunction with the Cures Act, is really driving FHIR adoption. So the Cures Act supports better access to health information and has added in some additional interoperability criteria into the existing Health IT certification program. So this Health IT certification program is voluntary for Health IT vendors, but CMS provides a financial incentive, which means that it is pretty widely adopted. If you're curious about the 21st Century Cures Act, there's a lot in here. These are the sections that are especially relevant for FHIR adoption. So the first section here talks about the certification needing to require publishing an API. The FHIR APIs are able to fulfill this need. The next section talks about interoperability and about trusted exchange frameworks, which are also coming online soon. Information blocking is in the next section, and FHIR also helps address this. And then the final 2 sections talk about some of the rationale for what the Cures Act is trying to do. And this really helps to summarize some of that. It's really designed to be patient-centric and allow patients access to their data. This is relevant from a research perspective because if patients have access to the data, they can potentially provide it for research, but also the same technology that allows patients to have access to their data and have access to an app economy for health-related applications also can be used for research purposes and for other interoperability purposes. This is a timeline looking at the implementation of some of these interoperability standards. I've called out 3 of them on the slide here. The first is US CDI. This is a set of common data elements for representing health data in the United States. It's not actually specific to FHIR. It's just a set of data elements. But we'll talk about US Core, which is a FHIR implementation guide that implements US CDI on top of FHIR. The second bullet here, the FHIR API, the deadline for implementation of this for certification was at the end of 2022. This means that the EHRs that are certified now have FHIR APIs that are available. The last item here, FHIR bulk export, is due to be implemented for certification at the end of 2023. So as of recording, we haven't hit this time frame yet, but pretty soon this will be available in EHRs as well. And this is interesting because it allows access to FHIR formatted data at the population level, whereas the FHIR API is typically more for a more patient-centric workflow. So I mentioned US CDI and US Core on the previous slide. Again, US CDI is a standardized set of health data elements for health data in the United States. And then US Core is the implementation that's aligned to US CDI on top of FHIR. So the US Core, the published version of this specification initially was in 2021, and then it's being updated every January starting in 2022. And a lot of other US-based FHIR implementation guides are actually based off of US Core. And this is helpful for researchers because if you are working on an implementation guide or you're using an existing implementation guide and it's already based off of US Core, it makes it a lot easier for an EHR vendor to actually implement if it's not already implemented. I'll talk now about FHIR's fit with other standards. So I already mentioned HL7 V2 and V3. I'll talk in just a little bit more detail about these here as they're still definitely in use and relevant. So like I said, HL7 V2 is around 30 years old. It allows for simple transfer of information, point-to-point messaging. It doesn't support more complex interactions. So for example, that paper that used Smart on FHIR to add custom clinical decision support directly into an EHR, that's not something that would really be possible using V2, but it is possible with FHIR. HL7 V3 was developed as a way to extend interoperability from V2 to allow for a lot more complexity. It also used some standard technologies like SOAP and XML that come from outside health IT. The idea of V3 was to allow for a lot more flexibility. Unfortunately, this additional flexibility also ended up with a lot of complexity for implementation. So V3 was not widely implemented in the same way that V2 was. But V3 did lead to clinical document architecture, or CDA, and that standard for clinical documents is more widely implemented. And then finally, FHIR, like I said before, is based off of some of the lessons learned from V2 and V3. So FHIR explicitly uses current web technology as much as possible, which is really useful for implementation. So software developers don't necessarily have to have deep health IT experience or specific experience with FHIR in order to pretty quickly get up to speed and be productive working with FHIR. And this is really useful for developing custom applications. It just makes it a lot easier to find people who can work on those applications. And it makes development of those applications more rapid because it uses standard technology that's already baked into a lot of the software development tools that software engineers use. This graph is from InterSystems. It's not based on real data. It's more of a gut feeling about adoption and mind share of these different standards. The bar that shows present day is actually probably not accurate anymore. The bar probably has already moved further to the right, where we see the adoption of FHIR really taking off, the adoption of some of these other standards and the mind share starting to decrease as FHIR takes over. And as the Cures Act comes into full effect, this bar is going to continue to move rapidly to the right as FHIR really takes over the mind share in the health interoperability ecosystem. one of the questions that comes up a lot is how FHIR works with other common data models specifically for research. So OMOP is an example of one of these common data models. It's pretty widely used. It's used for N3C and also lots of other uses in the literature. Um, and on the surface, a common data model like OMOP serves some of the same purposes that something like FHIR for research might. To talk about how these two technologies can coexist with each other, I'll talk a little bit about the OMOP on FHIR project. This is a project that helps to bridge between OMOP and FHIR and allow for bidirectional read and write capabilities. So going from OMOP to FHIR, this project allows for retrieval of the data stored in the OMOP relational data schema and converting that into FHIR resources. So this can be useful in an environment where you need to be able to send data in FHIR format already, or if for some reason it's easier to work with data in FHIR format versus trying to pull data out in a tabular format from the OMOP database. This technology also allows for standard FHIR queries to be translated into OMOP SQL queries, and then mapping and converting into FHIR resources. Going from FHIR to OMOP, this allows users to actually post FHIR resources to an OMOP server and then map those resources into the OMOP schema and save them in the relational database. So this is potentially a good way to load data into a OMOP relational database. So OMOP and FHIR can be used together like this. FHIR is definitely not meant to replace OMOP. It's a tool that can be used alongside OMOP and is potentially very helpful if researchers are trying to have research that spans across multiple sites, and those sites don't all have the same OMOP database in place. So in summary, for this part of the webinar, FHIR is an open standard for exchanging health data, which has been widely adopted, and it has untapped potential to enable and accelerate research, especially as adoption continues to pick up as the Cures Act goes into effect. FHIR may be useful in a number of different research workflows that touch EHR data or data from other systems that support FHIR. So some examples of this that we saw are integrating with clinical workflows like clinical decision support or patient-reported data. And with Smart on FHIR, you can actually integrate third-party applications directly into EHR workflows. FHIR is also useful in extracting data. So for example, using FHIR can be used to populate clinical trial case report forms. And this is nice because using FHIR is portable across institutions that have EHRs with FHIR APIs, whereas doing a one-off data pull might not be as portable. We also saw an example of phenotyping to develop portable phenotypes for developing patients of cohorts of patients across multiple sites. FHIR is overtaking some of the older standards that are already adopted in the health IT ecosystem. And this is great for research because FHIR is so much more accessible from a researcher perspective. And FHIR can peacefully coexist with other technology that's used for research, like CDMs, including OMOP. So for more information about this, we've developed a website, which is at the URL here on the screen and also at that QR code. This website covers a lot of the information from this part of the webinar and also goes into a lot more depth about some of these topics, including Smart on FHIR, terminology, creating FHIR implementation guides to customize and extend FHIR, and a number of other topics as well. In part two, we'll be getting into some more technical details on using FHIR for research. We'll start with looking at terminology and how terminology are used in FHIR. We'll then look at more details about FHIR resources and profiling in FHIR. And then we'll talk about the FHIR API and how FHIR can interact across different systems. Starting with terminology in FHIR. Uh, Using standardized terminology is really important for all health information technology, including research applications. So this allows researchers to exchange and organize health data in a consistent and reliable way. So for example, if a standardized terminology is used to identify conditions in a problem list, that facilitates using something like automated cohort building software to build a cohort based on the presence and absence of these conditions. If you don't have standardized terminology, you're relying on trying to parse plain text descriptions of conditions, which is much less reliable. Some of the common kinds of terminology or code systems that are typically encountered in the FHIR world are LOINC for identifying laboratory tests, SNOMED CT, which is a really broad health terminology system. Some of the applications for SNOMED include identifying the results of laboratory tests, but it also has lots of other things in it, like diseases and diagnoses. ICD-10 is another example. RX norm for identifying medications is another example of a terminology that appears in the FHIR world. And FHIR supports working with terminologies in a few different ways. So FHIR supports defining code systems. So if you need to define a custom code system that's not one of these standard ones, you can do that. You can map between different code systems with FHIR. So if you need to map SNOMED onto ICD, for example, that can be done with FHIR. And then FHIR allows for binding of a specific data element onto a specific subset of concepts from selected code systems. And we'll take a look at that now. So what I'm showing on the screen now is a screenshot of some of the data elements that are inside the patient resource in the base FHIR specification. This comes from the R5 version of FHIR. And I'm going to go into more detail on this later. For now, I want to just focus on this marital status data element. And we can see on the right side here that marital status is bound to this marital status codes value set with an extensible binding. So I'll explain what that is here on the next couple of slides. So starting with the value set that this is bound to. So if you click that link, if you click this link right here, it will take you to this web page here. And I've just copied the table from this web page onto the slide to make it a little bit easier to see. So this is the standard format for a value set. You have a computer readable code and then human readable display text that explains that code, a longer definition, and then a link back to the code system where the code comes from. So this might be a link back to ICD-10. It could be a link back to SNOMED or LOINC. In this case, this is actually an HL7 code system, specifically for marital status. And the codes are these single letter codes. So M for married, D for divorced, et cetera. If you look at the, this is just an excerpt. If you look at the full value set at this URL here, there's several more codes that just didn't fit on the screen. So what has happened with FHIR here in the FHIR resource for patient is that this value set was linked into the marital status data element. This value set pulled in codes from two different code systems. So on the previous slide, I was showing the code system from this, or the codes from this marital status code system. There's also one additional code, this unknown code, UNK, which comes from this null flavor code system. And again, this is another HL7 code system. And together, the codes from these two systems make up this value set. And that means that if you are populating the marital status data element, the codes that you're using to represent this concept should be coming from this value set. The binding strength is what defines should be coming from the value set. So in this case, we have an extensible binding. What this means is that if a code is in that specified value set, in this value set here, and the concept you're trying to represent matches up to one of those codes, then you must use that code. Otherwise, you can use a different code. So for example, engaged was not in that value set. So if you need to represent engaged, you can choose whatever code you want. A good choice might be the SNOMED CT concept for engaged to be married. And there are lots of other binding strengths. There's required, there's preferred, there's exampled. The definitions of these binding strengths are at this URL here. What this allows an implementer to do is to create a profile of a patient resource, and I'll show an example of this in a minute, and actually strengthen this binding, make it more restrictive to make it so that for example, if for a research study, you need to know marital status and it needs to be a specific set of codes based off of the data dictionary for the study, you can do that in a FHIR implementation guide. You can create a value set that has just those codes in it. You can bind it to the marital status data element. And then there are automated tools available that allow you to take FHIR data and verify that it actually conforms to your constraints. To make sure that it doesn't have any values for marital status that aren't expected. If you've created an implementation guide and go through this process, it gives you a really clear way to make sure that the data you're getting are already essentially clean. Makes it a lot easier to work with the data for analysis. Just to review the implications for research here, the FHIR specification describes where this data element, marital status, should be stored. It's in the patient resource, and it's in a field called marital status. The FHIR specification also describes how marital status is encoded. So in this case, it uses terminology. It has a preference for the specific set of codes that we just talked about. And like I said, if you need to limit this, you can do it with a FHIR profile. If you need to specify a custom set of codes, you can do that with a custom selection of codes, excuse me. You can do that with a value set. You can pull from multiple different code systems into a value set to get exactly the set of codes that you need. And finally, you can use FHIR to translate between different code systems. There's a FHIR resource called a concept map that's designed specifically for this. And that allows you to relatively easily describe in a computable way the mappings between two different code systems. I'll now talk a little bit more about FHIR resources and profiles. So as I mentioned in the first part of the webinar, resources are the building blocks of FHIR. They act as customizable templates within the general FHIR framework and can be put together to solve a specific problem or meet a specific use case. The resources in the base FHIR specification are designed to be very flexible. So for example, you won't see a lot of required value set bindings in the base FHIR specification. I'm actually not sure if there's any in there. And that's because required binding really limits what the resource can be used for. If you have a use case that needs to use a different value set, you just wouldn't be able to use that FHIR resource. So the base FHIR specification tries to be as flexible as possible to avoid this problem. Almost every data element in the base FHIR specification is optional, even information that may be critical for health IT use cases. For an EHR, having a patient's name and date of birth and address are pretty critical, but FHIR doesn't require that those are filled in. That kind of requirements are done downstream with use case specific implementation guides. The FHIR resources by themselves are not necessarily useful because of this flexibility. So by using profiles to add constraints and to add extensions to supplement the existing resources, you're able to really customize FHIR to meet your specific needs. There are 157 FHIR resources in the R5 release of FHIR, things like patient, which we've already seen, other resources like diagnostic report, practitioner, and location may be useful as well. There's many, many more. And along with selecting those resources, defining profiles for those resources to add constraints and extensions, this allows for essentially the selection of the data elements that are needed for a given use case, whether that's a research use case or another health IT use case, and get that data with FHIR without having to get all the data in the EHR. So to talk a little bit more about what is a resource, I showed in the first part of the webinar that screen that had a list of just a subset of some of those 157 resources. To go through this in a little bit more detail, some examples of FHIR resources include administrative resources like patient and practitioner organization, which could be something like a hospital. Location. So location is useful if you have, rather than a hospital as an organization, you have, let's say, a pharmacy. And that pharmacy has multiple different branches. So you can use the locations resource to describe those different branches. There's also resources related to payment. So coverage for insurance and claims are also FHIR resources. There's a number of clinical concepts, allergy intolerance, condition, family member history, and care plan are some examples of that. And then FHIR includes a number of infrastructure resources. So we've talked about profiles already. There's also documents and compositions. Compositions allow you to bring together a number of FHIR resources to essentially tell a story. Capability statement is a FHIR resource that's used to describe the capabilities of a FHIR server. So there's a lot of different resources that are available. And the best place to learn more about that is actually going to the FHIR specification and looking at that page that I showed a screenshot of earlier that lists all the resources in different categories. Some non-examples of resources. So the scope of the resources in the FHIR specification are very intentionally chosen to be the right size to be useful without being too narrow or too broad or too specific. So some examples of things that don't make sense as resources. Patient name is too small to be a resource. That's just a data element or several data elements actually inside the patient resource. Electronic health record is too big. That's really a collection of a whole bunch of different FHIR resources, and having it as one resource would just be too unwieldy. Blood pressure is too specific. Makes more sense to generalize this and use an observation resource to include blood pressure and lots of other observations about patients. And then intervention is too broad because this might include multiple medications or procedures. And it's better to use something like a composition to bring together multiple resources that represent an intervention. So we'll look again at an example of the patient resource in the FHIR specification. So again, this is a screenshot of a table that appears in every single FHIR resource in the FHIR specification. This is the URL here if you want to open this up yourself. And I'll actually open this up in a second in the web browser to show what it looks like. Inside the patient resource, we have a number of data elements. This just shows the top several on the page. Each data element has a name. It has some flags, and I'll talk a little bit more about the flags in a minute. It has cardinality, which defines how many values are allowed to appear for a given data element. So for example, name can have, it can be empty or it can have multiple values. That's what the star means. Because a person can have different names, like if they changed their name when they were married. We also have something like birth date, which can either be blank or it can have one value because it doesn't make sense to have multiple birth dates. Each data element has a type. So some of these types are simple types like Boolean or date. Which will be familiar to people who have a informatics or a computer science background. There's also some more complex data types like human name, which can account for the complexity of how human names are represented. And if you go into and look at human name, this allows you to split a name up into a family name and multiple given names, or just a single string that can have the entire name in one data element. So there's lots of examples of more complex data type like this within FHIR. Each data element has a short description here that appears alongside in this last column. And by clicking on the name of the data element, if you're in the FHIR specification, this will open up a more detailed view that shows a longer description of every data element. So I'll switch over here to the FHIR R5 patient page in the specification. And I'll just scroll through this quickly here. So this is where I got that screenshot from. You can see the screenshot cuts off right here, but it keeps going. There's lots more data elements here. And then if you click into one of these data elements, it will go into this page that gives you more information about the data element, in addition to some commentary, other requirements, etc. You could also click on the type to go to a page that describes the type of data elements. So for complex types, this is useful because it will actually go through and show all the different elements that are essentially sub-elements within this complex type. So I've mentioned FHIR profiles a few times now. So if resources are the basic building blocks of the FHIR specification, then profiles are the way that these resources can be adjusted for a specific use case. Profiles can be used to both restrict and extend FHIR APIs, resources, and terminology. They do this through a number of different ways. So I mentioned cardinality on the previous slide. So here we see a cardinality of 0 to infinity or 0 to 1. In a profile, you can actually adjust these cardinalities to make these more constrained. So if you wanted to, for example, make birth date required, you can change this minimum value to a 1 here, which means that there would have to be exactly one value populated for birth date on a FHIR formatted FHIR formatted instance of the patient resource. You can also specify value sets and value set bindings with profiles. And profiles are typically not considered individually, but are grouped together and published as an implementation guide. So here's an example of a profile of the patient resource from that US core implementation guide. So US core is the FHIR implementation of the US CDI set of common data elements for health data in the United States. And I want to point out a couple things that appear in this, this profile of patient. So the first are these extensions here. You'll see 3 different extensions. The first 2, US core race and US core ethnicity, are used to represent race and ethnicity, which are very common data elements in health data in the United States, but are less common in other jurisdictions. And for because of this, race and ethnicity are not included in the FHIR specification patient resource. So they have to be added with extensions in US core because they are so common in the United States. And what these extensions do is they provide a consistent way for implementers of US core to represent these data, both the names of the elements and also any relevant value set bindings. Those can all be included within the extension. So you really get the same benefits that you have in consistency in the FHIR specification by adding extensions on, but it's limited just to the implementers that actually implement the implementation guide where the extension is described. So in this case, all implementers of US core would implement these US core race and US core ethnicity extensions, and that would provide a consistent way to handle these data for those systems. I also mentioned before setting the cardinality of an element to make the element required. So we see here previously when we were looking at just the patient resource in the base FHIR specification, name was just at a 0 minimum. The US core profile raises this to a 1, making name required. So this has some implications for research use cases. Might actually not be able to use US core if you don't want to have patient name in the data. So you might need to fall back to using a separate profile of the base patient resource. But fortunately, because name is part of that base FHIR specification, it's easy to still work with that and to remove that in your own profile of patient. the last thing I'll note here, so these red S's, this is a flag called must support. This is part of the metadata that a profile can add to a FHIR resource. And must support is a flag that has a use case specific meaning. Typically, it means that the systems that are implementing the profile need to have some way to meaningfully process the data element. So this might mean populating the data element or being able to read the data element and display it. So US Core has added must support to a number of elements here to indicate that these are important data elements for the systems implementing US Core. FHIR implementation guides are a collection of profiles and other resources that are specific to a given use case. So just like profiles, implementation guides can restrict and extend FHIR. Implementation guides are often produced by FHIR accelerators. Accelerators are programs that HL7 has established to try to drive adoption and implementation around a specific use case. You see Vulcan on the slide here. Vulcan is a FHIR accelerator that's specifically focused on clinical research. There are a number of other accelerators as well. There's an accelerator called Codex, which is responsible for working on this M-code implementation guide on the right here. And the M-code is an implementation guide that focuses on collecting oncology data. So if you're interested in doing oncology research, M-code may be of interest to you as a way to represent the critical data for that work using FHIR. There are 205 FHIR implementation guides that are registered with HL7. There's lots more implementation guides out there as well that are not part of HL7 and part of the HL7 process. US Core is one of those implementation guides that's registered with HL7. And if you Google US Core FHIR, you'll be taken to a page on the HL7 website, actually, where that US Core implementation guide lives. So in the last section of this presentation, we'll spend a little bit of time talking at an even lower technical level about how FHIR can be used to interact with other systems. So this is probably going to be of most interest to people who are actually planning on working hands-on with FHIR data, either informaticists who are extracting data from FHIR endpoints and then working with it, or software developers who are developing custom applications using FHIR data. But it's still good for generally to have an idea of what's going on under the hood when we're talking about exchanging data in FHIR format. On the screen now is an example of an instance of a FHIR resource. This is in JSON format. I'll show XML format in a second. And where I've been talking about FHIR clients requesting data from FHIR servers, the FHIR server sending back the data that's been requested. This is an example of what the FHIR server might send back. So the data format, again, is JSON. This is a common data format that's used very widely for web technology outside of health IT. It is somewhat similar to the table we were actually just looking at in the FHIR specification for patients. So in JSON, we have each element name. These are the same element names that we saw in that in that table we were looking at a little while ago. And then we have the value for that element. So in this top section, these metadata elements actually don't show up in that table for the resource we were looking at, because these just appear in all instances of FHIR resources. So this tells you what resource type you're looking at, the ID of the resource for the system that produced it, and then additional metadata if necessary. There's this text component, which provides a human readable summary. If you're familiar with HTML, you'll see a little snippet of HTML here. And the idea is that this can be rendered directly by a web browser or an app to show a human readable summary of the content of the FHIR resource without having to actually parse through the entire instance of the FHIR resource here. Now we get into to the data from that table of the patient resource we were looking at a little while ago. So first we have any data that's from extensions. In this case here, we have a patient birth time extension. So the patient resource in FHIR just has a date for birth. It doesn't have an actual birth time, but HL7 provides an extension to represent a specific time of birth if that's important for your use case. And this is what that looks like here. And then we get into the standard data. So these are the data elements that we saw a few slides ago in that table of data elements for patient. So we have identifier, active, we have name, and this is an example of that hierarchy. So remember, name is a human name, and that can have different components like a family name and a given name. So we can see that hierarchy in action here. For some of the simple element types, we have just a string here for the gender. We have a date for the date of birth, and we have managing organization here, which again, this is a complex data type that provides a reference to another FHIR resource for an organization, and then a human readable display name for that organization. So looking at the same resource, this is the same data, but it's structured in XML format. XML is another commonly used data format. It's not just a health IT thing. It's also used widely on computer systems, both for the web and also systems that are not web enabled use XML. If you recall, V3 uses XML as well. So this is a technology that's been around for a while. It can be a little bit more difficult to work with in JSON. So a lot of the work that's done practically with FHIR data uses the JSON format, but you can convert losslessly between JSON and XML. And it just provides a different way of representing the same kind of data. So these are the two data formats you're likely to encounter if you're actually working with FHIR data, if you're requesting it from a FHIR server. There are some other formats too, but they're less common. And we see the same structure here. We have metadata at the top. We have a human readable summary. We have the extension data, and then we have all the data that's part of the standard data elements here. I'll talk a little bit more about the RESTful interface for FHIR now. So if you recall back to the first part of the webinar on the slide that showed the FHIR client and the FHIR server, the FHIR client and the FHIR server communicate over REST. This is the same technology that's used by web browsers and web servers. If you type in HTTP in your web browser, you're sending a RESTful request. Web browsers use a GET request by default to read data off of a server. FHIR does the same thing. But FHIR also allows for creating data or updating data or deleting data. And each of those operations has a HTTP verb as well. So post for creating, put for updating, and delete for deleting. When you're requesting data from a RESTful server, you have to provide the URL for that server. So this would be the URL to the FHIR endpoint that's part of an EHR, or it could be part of another server like the Kids First server, which serves research data in FHIR format. Additionally, when making a request, you would typically send some HTTP headers. This is how you actually say which data type you want. So if you want JSON, you can request application/FHIR plus JSON, or application/XML if you want XML. And then you can get the, you can send additional information in the body of the request. So taking a look at what this actually looks like. So here's a request. We have the get HTTP verb. We have the URL for a server. In this case, it's this open happy testing server. We have the endpoint is this base R4 endpoint, referring to the R4 version of FHIR. We have the resource that we're interested in this case, patient, and then we have the ID of the record that we want to retrieve. And then in the response, we get a 200 code, which is the universal OK code for HTTP responses. We get the content type, which is JSON. And then we get the JSON, that same format we saw a couple slides ago. We have the same ID here that we requested. We have the resource type identified here as patient, metadata. Hopefully this includes the last updated dates. So if your application needs to know whether it needs to update its internal data store based on the response from the server, this is one way that the FHIR server can provide this information. And then we have the same data elements we've been talking about. So we have name, we have gender, we have birth date. In this example, we don't have lots of the other data elements, but typically when you get a FHIR instance from a FHIR server, it will have a whole lot of elements that are populated. So the last technology I'll talk about here are the set of smart technologies out of Boston Children's Hospital. These are technologies that were developed and then moved into the HL7 standards process. I've already mentioned Smart on FHIR a few times. Smart on FHIR uses, again, this common web technology, OAuth and OpenID Connect, to provide authentication and authorization for third-party applications. I'll talk a little bit more about that on the next slide. CDS hooks are another related technology, which allows for actions to occur when something happens inside the EHR. So for example, if a certain thing happens inside the EHR, you can hook into that with a CDS hook and then suggest a Smart on FHIR application or trigger some kind of other action based off of what's going on in the EHR. And this provides a mechanism for being able to trigger integration with things like a Smart on FHIR application. I mentioned bulk data back when discussing the Cures Act, and at the end of 2023, the implementation of bulk data as part of certification with ONC. So bulk data provides a mechanism for getting population level data out of a FHIR server. As we saw here, a lot of FHIR APIs are more focused on getting a specific patient or a specific subset of patients, and bulk data allows for just accessing a greater set of patients all at once. Typically, this would be used in something like a backend process that's doing some kind of bulk processing of FHIR formatted data. And finally, smart health cards is a technology that you may be familiar with if you have a QR code on your phone for vaccination information. That's using smart health cards, most likely if you're in the US. And that uses FHIR under the hood to store the clinical data in the smart health card. So I'll talk just a little bit more here about Smart on FHIR. This slide also shows the acronym for what SMART means. Smart on FHIR provides a way for applications developed by third parties to connect deeply into an EHR, and it assures adequate security to protect personal data. So for example, if I log into the health app on my phone with my patient portal credentials, that can authenticate with the patient portal and pull data using Smart on FHIR, and it only gives me access to my own data. It doesn't give me access to other patients' data. Smart on FHIR is helpful because it decouples the EHR data from the app builders. So rather than having to have all apps built by the IT vendor that creates the EHR, third-party application developers can come in and get access to that EHR data in a standardized way. There's multiple ways that Smart on FHIR can integrate with an EHR or from outside an EHR. So the example I just gave of logging in on my smartphone to get access to my own patient data, that's an example of a standalone. You can also have EHR launch, which is how that integration that we saw earlier in the paper integrating type 2 diabetes clinical decision support tool into an EHR that used EHR launch. And then there's also a mechanism for Smart on FHIR to use launch on the server side to get access to bulk data. And what Smart on FHIR enables is really using the EHR as a platform for different apps. These apps are not necessarily limited to research. They can be lots of other things. They can be patient-centric or provider-centric, or can provide other use cases as well. And the idea is that you can write a Smart on Fire app once and then be able to run it across multiple EHRs without having to do a lot of modification of the underlying code. So in summary, in the second part of the webinar, we talked about the basic building blocks of FHIR and went through patient in some detail. We talked about the data elements that are defined by resources, how these data elements have names and types, and they could be bound to terminology. We talked about implementation guides, how implementation guides can be used for extending FHIR to meet a specific use case. This can be done by adding constraints like required elements or specific terminology, and also by adding extensions if the base FHIR specification doesn't provide the data element that you need. You can make your own IG. If you go to the URL right here, there is information about creating IG specifically for research use cases. And then we also talked about the standard web technology that FHIR uses and how this can facilitate interoperability and could potentially be used to facilitate research use cases as well. So again, this URL goes into more detail about the web technology, and this QR code will take you to the same website.